In our last video, we introduced the idea of sound and something called standing waves. Standing waves being a wave that's oscillating between two different positions. In this video, we're going to extend that to the next step and talk about how those standing waves can form something called a harmonic, and then how those harmonics can be used to design and predict the results for instruments. So to start us off, let's just review this idea of a standing wave. Standing wave, remember, is a wave that is going back and forth between these two positions, and it's repeating continually. The key feature of this standing wave is that there are some parts of this wave that do not have any amplitude at all. We call those the nodes, and some parts that have a maximum amplitude at all times. Those are called the antinodes. We are going to use this now in the form of an instrument to talk about how that is going to result in different sounds that an instrument can produce. And the simplest instrument that we're going to talk about is a bugle, or something along the same lines. A bugle produces sounds, produces different pitches using something called harmonics. That a bugle has a feature that is unique from a trumpet, that it doesn't have valves. There is no way to change the length of the space. So the only way that you can get different notes on a bugle is by changing the amount of energy, the buzz in your lips, and increasing the amount of energy that's resonating in that space. When you do that, you have a certain number of notes that are available to you. You're confined to these notes because the physics that underlies that is that there are only certain numbers of standing waves that can exist. So here we have all the different combinations of standing waves that would resonate within this space. And each of those is getting progressively more complex, and we'll talk about that. But each of them reduces the wavelength and increases the frequency. So you can see that the pitch of the note increases as it goes. And because of this restrictive scale, there are only certain numbers of songs that a bugle can play. So this song is very famous as like the Wake Up Call. But there's also a very famous song, Taps, that's played at a lot of military funerals. That is using this harmonic scale. So to give an example on how this doesn't have to be a bugle, as long as the physics that underlies it works off of harmonics, you can play either of these songs with any instrument built on the harmonic scale. So I'm going to turn it over to myself. What I have here is a flexible tube with an open end on both sides. This can operate like an instrument if I create an excitation of air across one end, very similar to if you were blowing across the top of a bottle or a flute. The energy going across there creates a wave that resonates with an antinode on both sides. And the faster I go, the higher the pitch becomes. Now this plays the harmonic scale. Each one of these notes is a different harmonic, and the scale is the same as a bugle or any other instrument that is playing without valves or keys. So I should be able to play any song that a bugle can play. This is my attempt at playing Taps. All right, there you go. This instrument operates on the harmonic scale. It can play any song that a bugle can play, provided it's given enough time. So let's talk about the physics behind this and why that works, that flexible tube can operate just like a bugle. What is the same about both of them? Well, it turns out that they actually have a similar construction in the fact that there's an open end on both sides of that resonant space. So we're going to call this type of instrument an open pipe system. And the rule for an open pipe resonance is that you need to have an antinode on both ends. So each open end has an antinode for the standing wave that's resonating inside it. The simplest version of a standing wave that has an antinode on both ends is one that only has two antinodes, and it looks like this. Now, if I want to figure out how the length of this tube is related to the wavelength of that particular wave, I can look at one side of this standing wave and see that it only completes half of a full wavelength. So I would call that 1/2 of a wavelength overall for the length of that tube. For it to complete a full wavelength, it would need to go down and then come back up and come back up to the other side. We would call this the fundamental frequency, or the first harmonic of an open pipe system. That's the lowest note that you can play in that system. The next lowest note is our second harmonic, or our second resonating position. It still has to have an antinode on both sides. So the next complex setup looks like this. It has 3 antinodes, 1 in the middle and then 2 on each side, or 1 on each side. This one, if I look at one complete side there, I can see that that's 1 full wavelength, or 1 lambda, or just lambda is equal to L. My third resonating position is more complex still, fitting in more standing waves. So now I see that my full wavelength is here, and then I have another half of a wavelength. So that standing wave occurs when there's 3.5 wavelengths that fit within the length of the tube. So this open pipe system is similar to that flexible tube and similar to a bugle. Another type of instrument that exists is called a closed pipe system. And now they don't look this simple. This could be anything like a pop bottle. If you're blowing over the top is an open pipe. So there's an open end there, and then the bottom is closed. That isn't exposed to the external air, the outside atmosphere. So we're going to see this end here is our closed end. This end is our open end. When I say closed pipe system, I don't mean that both sides are closed. Only one of those sides needs to be closed. And the rule there is that that closed end gets a node, and the open end is an antinode. The node allows it to reflect off of that closed end surface. So the simplest standing wave that matches this configuration is one that has a single node and a single antinode. It looks like this. Now this is a pretty simple wave. If I look at just one side there, that is actually only 1/4 of a wavelength. For it to be a full wavelength, we would need to come back down to the equilibrium, then go down to the minimum and back to the equilibrium. My next resonating position looks like this. Still has a node and an antinode, but we can fit more of a standing wave in there. This is actually 3/4 of a standing wave. That is not 3/4 of a wavelength. That's not one complete wavelength quite yet. And then my third resonant position looks like this, where I've got 2.5 standing waves, which results in 1 complete wave and then another quarter. So in fractional form, that would be 5/4 of a wavelength, or 1.25 times the wavelength is equal to the length of that pipe. Now, both of those instruments were basically wind instruments. It's a column of air that is resonating at that natural frequency. Well, another common style of instrument is a string instrument, like a guitar or this ukulele here. Of course, that produces sound when the string vibrates back and forth. And an important feature of a string vibrating back and forth is you can actually change the wave speed down the string by changing the string's tension. So there are a couple different ways that I can change the note that's operating on a string instrument. The first way that I can do this is I can increase the tension. That's done with these tuning pegs here. So if I pluck that, I can increase the tension, which changes the frequency by changing the wave speed that's happening within that string. The other way that I can change the frequency of the string is by changing its length. So I can decrease or increase the length by pressing my finger on the different frets. And this is primarily how a guitar or ukulele is played, making different chords by changing the length of the string and then ultimately changing their frequencies or the pitch that they're producing. So let's look at what the standing wave diagrams are going to look like for these types of instruments. In this case, if I look at my ukulele, the string is fixed here at the top and it's fixed here at the bottom, which means that they cannot have any amplitude. They're fixed. That's just the design of the instrument. So we have to have a node on both ends. So starting with the simplest wave that has a node on both ends is one that just has 2 nodes. It's one standing wave, which is half of a wavelength. The next most complex, the second harmonic of this string, is one that has a node on both ends and a node in the middle, so it has 2 standing waves. That is 1 complete wavelength, or 1 lambda, or just lambda. And then the third harmonic, the third resonating position, looks like this. That's 3 standing waves, or 1.5 times the wavelength, 3 halves of the wavelength. Okay, so all of these little equations that I'm writing on the side are not something that I expect you to memorize. My recommendation is that you memorize the conditions, draw your picture, and then interpret the picture. So you need to know these end conditions. You need to know that for a closed pipe, that means a pipe closed on one end, open on the other end. That results in a node and an antinode. And you can draw in the harmonics that match that setup. An open pipe system is one with an antinode on both ends, and a string is one with a node on both ends. If you go back and look at it, our equations were actually the same for an open node and a string. As long as it's the same configuration, antinode, antinode, or node, node, you're going to get the same 1/2, 1, 3/2 sort of setup in your harmonic scale. So you should be able to draw all of these pictures. Again, this isn't a task of memorization. You shouldn't be able to have to memorize photographic memory what this picture looks like. Rather, what you should be doing here is you should remember that an open has an antinode, antinode, closed is node, antinode, and string is node, node, and then draw in the waves that would fit those conditions. So if you remember back to pitch and frequency, a higher pitch sound has a high frequency, a lower pitch sound has a low frequency, and that's fairly intuitive. Well, we can use that concept to create different pitches. And there are a couple different ways that we can create the different pitches. One is by using a tube like I did to play taps. In this case, I have the same length of the tube, and I'm just adding more energy to produce more harmonics. The other way that you can do this is you can change the length of the tube and keep the same harmonic. So here, if you have a pipe organ has very different lengths of pipes, and each one produces one given note. Well, it's the same waveform shape that's resonating in all of them. It's all their fundamental frequency, but since they are different lengths, that fundamental frequency results in shorter and shorter wavelengths as you're getting smaller and smaller. So the two ways that you can change the pitch is by either changing the length of the tube and keeping the harmonic, or keeping the length of the tube and changing the harmonic. So let's look at this in terms of a problem. So if we are trying to calculate here, an open organ pipe is 2.1 meters long. That's a pretty long organ pipe. That's over 6 feet long. And the speed of sound in the pipe is 341 meters per second. That's roughly room temperature speed of sound. What is the fundamental frequency of the pipe? So from just the length of the pipe and the speed of sound on that day, you should be able to tell me what note that organ pipe is going to be playing. So to do this, you're going to use this equation that the wave speed is equal to the frequency times the wavelength to solve for the frequency. I'm given the wave speed, but I'm not directly given this wavelength. I'm given a length, but that's not the same thing in this case. Instead, what I need to do is I need to analyze what that organ pipe looks like. This is an open pipe system. It will always be told to you, you don't have to memorize every single instrument. And in an open pipe system, if we're looking at the fundamental frequency, that's the first harmonic. Fundamental frequency means first harmonic. If you're ever in doubt, just assume first harmonic, assume that it's the fundamental. So that means it's the simplest waveform that fits an antinode on both ends because it's an open pipe. That looks like this. I know from when we looked at it before that this length here is related to the wavelength if I can count how many wavelengths there are. So this is L, it's not lambda, it's not the wavelength. Instead, we know that L is equal to half of a wavelength because there's half of a wave that fits inside this first harmonic, this fundamental frequency of an open pipe. So if I know that that 2.1 meters is L, I can solve this for lambda and then get a little farther in calculating my frequency. Rearranging this for lambda, lambda is just 2 times L. To get a full wave in here, I would need double the length of this particular pipe. And that pipe was 2.1 meters. So 2 times 2.1 is 4.2 meters. This is lambda. This is my wavelength. So I can plug that in here, rearrange this equation to solve for the frequency. The frequency is the wave speed divided by the wavelength, which is 341 divided by 4.2 to give me a final answer of 81.2 hertz. That's a pretty low note, which would make sense if you have an organ pipe that is longer than I am tall. Next example I want to look at is a string instrument of a similar sort of thing. Here we have a note being produced on a violin that has a string length of 40 centimeters and a wave speed in that string of 250 meters per second. So what is the first harmonic, this fundamental frequency of the note? Well, a violin is set up very similar to my ukulele here. The strings are fixed on both ends. So we know that if we have this information, we can find the wavelength by looking at the string itself. The string has these fixed ends, which means we have to have a node in our system. This is the first harmonic, so it's going to be our simplest wave with just a node on either end. And we know that the length of this string is 40 centimeters. Since we're using meters per second down here, we're going to convert that into meters, knowing that the length from one end to the other contains half of a wavelength. So if I want to find lambda from this length, I can do the same thing that I did before. Lambda is equal to 2 times L. The length in meters is 0.4, so 2 times 0.4 is 0.8. Plug that in for my wavelength. Then solve this for F. 250 divided by 0.8 gives me a frequency of 312.5 hertz. So again, if I know the length and I know the speed, I have enough to figure out what the resonance of that string is going to be. What note will it play? All right, we have now seen an open pipe system. We've now seen a string system. Let's analyze now what a closed pipe system would look like. And to do this, I'm going to pass it back to myself to walk through an example that's actually a pretty cool way of finding a resonance space.
It's a 341.3 hertz tuning fork. And in my setup here, I've got a tuning fork and a rubber stopper. This rubber stopper can be used to strike the tuning fork. If I hold it up next to the microphone, you can potentially hear the note that's being played. This one is the note F. It's a 341.3 hertz tuning fork. And I can hear it if I put it up next to my ear, but it's not very loud. I can create a much louder sound if I use a resonant space of air vibrating in this column. This is going to operate as an open pipe system with one end and a closed pipe system with the other. So we've got an open end here at the very top and a closed end wherever this hits the water boundary in this graduated cylinder. So the farther I pull this out, the larger this closed end tube is going to be. Now, if I take a tuning fork, strike it, and then play around, I can often find the resonant frequency space. It's right about here for this particular tuning fork. And to make it so that you can hear that, I'm going to try to hold this microphone a little bit closer. So you can find that resonant space. This is the first fundamental frequency for this particular tuning fork. The second resonant position would be a little bit higher up. The third would be higher still.
All right, so let's look at what the wave is looking like in this particular example. That tuning fork that I had outside is a fixed frequency, which means if the speed of sound is the same through air, it has a fixed wavelength as well. So I'm not changing the wavelength. The wavelength is existing regardless. But if I want to resonate this sound, I need to set it up so that it has the closed pipe resonant conditions with an open end having an antinode, so the open end is on the top, and a closed end having a node, which means I need to raise this out of the water until it hits the point that the node is right on the surface of the water and then matches that resonant space. That's basically the same as taking an instrument of that length is going to produce that note. Here, I already have the note, so if I want to resonate it, I need an instrument of that length. Well, if you look beyond here, that continues, that I can actually go to the next harmonic with the same note and just make the tube longer. So if I increased the length of the tube, eventually I hit that next node, which then resonates that sound again. So let's look at what that looks like with some numbers here. You find an unmarked tuning fork in your collection. You notice that the smallest length for resonance is 12 centimeters. That means it's this point here when it first starts resonating at its smallest length. The speed of sound is 345 meters per second. What is the tuning fork's frequency? All right, if I want to find the frequency, I'm going to use the same equation that I did in the last couple of problems. Frequency is the wave speed divided by the wavelength. I know the wave speed, but I'm not given directly the wavelength. I'm just given the length of this tube. So let's look at what that harmonic wave drawing looks like. This, we said, was a quarter of a wavelength, which means the length, 12 centimeters, here is going to be, multiply that by 4 to get the wavelength. This 12 centimeters is measured from the open end to the closed end, in this case just the surface of the water. So 12 centimeters converted into meters is 0.12. So 4 times 0.12 is 0.48. That is the wavelength of this wave. Because the wavelength would be how long would it have to be to go one complete wave. Only a quarter of that wave is actually above the water. So if I plug that in for my wavelength, 345 divided by 0.48 is telling me that my tuning fork has a frequency of 718.75 hertz. That can tell me, that can map me to the note that it's actually producing. The next question then is, what should the length of the tube be for the second resonant position? Second resonant position would mean I keep lifting it up until it resonates again. In this case, now I have 3/4 of a wave that fits in there, 3/4 of a wavelength. If I rearrange that, or if I'm trying to figure out what the length of the tube is. So now I just want to find L. I'm not given L, but I know from this initial problem that the wavelength was 0.48. I could also work backwards and figure out the wavelength from the frequency of the tuning fork I just calculated, but it would come out to 0.48 anyway. So that means that it's basically going to be just 3 times longer than the tube was initially. So 0.36 meters, 36 centimeters now above. 12 centimeters, 3 times that would be 36, because we went from a quarter of a wavelength to 3/4 of a wavelength. In this video, you should be able to come from this identifying and labeling the node-antinode conditions for a standing wave diagram, for then the end conditions of node, antinode, open, closed pipes, or vibrating strings. And then you should be able to calculate the wavelength or instrument length of a standing wave for different harmonics and figure out what note does it produce, or how long would it have to be to produce this particular note.